guys, welcome back to the channel. In this video we are going to discuss another problem on Nyquist plot, and this type of questions frequently come in exams. So let's start. So the first step to draw a Nyquist plot is to find out the pole and draw a contour. So here the poles are 0, 0, minus 1, minus 1 by 2. So here the poles are lying on 0. That's why we have to draw the contour leaving the origin, and this will go to a plus infinity, and from infinity it will return to minus infinity. This is C1 and this is C2. Again from minus infinity it will go towards origin, but it will not touch the origin, and this is C3. And finally from here to here it will cover a path. This is called C4. So in the previous video we discussed that there was no pole at the origin, but in this problem there is a pole at the origin. That's why we took 4 contours. And next is to draw C1. For C1 we have to see the type and order. So the type are the number of S which are having no plus or minus with it. So there are 2 S, so the type is 2, and order the total number of S in the denominator, that is 1, 2, 3 and 4. So 4. And for this we will draw the diagram. The type always starts from 0. This is type 0, this is type 1, and this is type 2. And the order always starts from 1. This is order 1, order 2, order 3 and order 4. So the diagram is starting from type 2 and ending to order 4. This is type 2 and this is order 4. Type 0, type 1, type 2, orders 1, 2, 3 and 4. So we will draw it from infinity and it will get ended up with order 4. So this is C1, and now we are going to find the distance between the origin and the point which is intersecting the imaginary axis. To do this, we will first substitute S is equals to j omega. Now we will substitute S is equals to j omega in the given equation, that is j of S is equals to 1 by S square 1 plus S into 2S plus 1. So here it will become g of j omega by into 1 by S square, j omega square 1 plus j omega 2 j omega plus 1. And if we convert it into standard form, this will become 1 plus j omega 1 plus 2 j omega. And if we find the magnitude, we will get, this is omega, 1 plus omega square and 1 plus 4 omega square. If we find the phase, we will get minus 180 degrees, because here we are having j omega square. So minus 90 into 2, minus 180, and minus tan inverse of omega and minus tan inverse of 2 omega. Now we are going to rationalize this equation and we will find the imaginary and real parts. So g of S is equals to 1 by j omega square 1 plus j omega and 1 plus 2 j omega into just leave that 1 minus 2 j omega minus j omega and 1 minus 2 j omega. So if we solve the numerator, so this j square will become minus 1. Now here you can see that j square is minus 1, and if we will get So finally we got the equation like this, and now we will separate the imaginary and real part out of it. So as we got, now we will separate the real and imaginary part. 1 plus omega square and 1 plus 4 omega square. This is, now as the diagram was touching the imaginary axis, we will make the real part equal to 0. So the real part is 2 omega square by 1 minus 1 and omega square. This is equals to 0. Now we will substitute this omega value into the magnitude. The magnitude is equals to omega 1 plus omega square 1 plus 4 omega square. We will get 1 by root 2 into 1 plus 1 by 2 4 into 1 by 2. This is 2, and we will get 1 by root 2. This is root 3 by 2 into this is root 3, and if we solve it, we get root 3 and root 3 is 3, and root 2 and root 2 is 2. So we'll get 2 by 3, and 2 by 3 is equals to 0.67. So this is the distance of the point of intersection on the axis, that is this imaginary axis, from origin. Now as we have got this, we will go to the next step, which is to calculate C2, and here we will substitute S is equals to limit of capital R tends to infinity R into J e to the power of J theta, as our initial equation is S square 1 plus S and 1 plus 2S. We will substitute as 1 by R e to the power of J theta square 1 plus R J theta 1 plus 2 into the power R into the power J theta. And now let's take a division in this paper. So as we will substitute R equal to infinity, this will become 1 by infinity, this will become 1 by infinity, and we will separate these terms. Then we will get 1 by R square 4 R to the power 4 4 J theta, and 0 plus 1 0 plus 2. So now this will become again infinity, so we will get into e to the power 4 J theta. This is 1 and 2. Now this is 1 by infinity, so we'll get 0 e to the power of minus 4 J theta. So now this is the magnitude and this is for phase. Never do the mistake to round off everything. Never do the mistake to round off everything and convert it into 0, because in the final we will get magnitude as 0 and we will get something as phase. So for C2 path, the theta is going from plus 90 to minus 90. So as you can see here, this C2 is going from plus 90 to minus 90, and hence theta is equals to 90 to minus 90. And when it is multiplied by minus 4, then we will get minus 360 to plus 360. As we got minus 4 theta from minus 360 degrees to plus 360 degrees, we will draw the contour for it, and this is for C2. Now this is 0, this is plus 90, this is plus 180, plus 270, this is plus 360. Again this is minus 270, minus 180, minus 90, and minus 360. So we are starting from minus 360, then going towards the positive side and ending with 0, and then from 0 to plus 360. So this is minus 360, and then we'll come to minus 270, then minus 80, then minus 90, and 0. From 0 we'll go to plus 90, plus 180, plus 270, and plus 360. And then we'll end up with 0. Then again we'll go to positive side, that is plus 90, then plus 180, plus 270, and plus 360. So this is an anti-clockwise contour, and the magnitude is equal to 0. But to understand it, we are drawing it like this. In the main graph, we will draw it as small as possible. Now for C3, this is the mirror image of C1. The C1 was, you can see the C1 is like this. So we'll get the C3 as like this, as it is. And this is again 0.67, and this is coming from my infinity and ending up to 0. This is imaginary axis and these are the real axes. Actually I have a correction here, that this is C1 and this is C3, so we have to take the mirror image horizontally, and here I took the mirror image vertically. So this is wrong, and we have to draw it like this, and the arrows will come out of it. So this is the C3 diagram, and let's proceed to the next steps. Now for C4, again we have to do the substitution of S as C4, S as S is equals to limit small r tends to 0, small r into e to the power of J theta. So the initial equation was 2S plus 1, and now we will substitute it. We will get r equal to 0. So it will get deleted, and we will get r square, this is turned to 0, e to the power J theta whole square, 0 plus 1 and 0 plus 1. So we will get it as 0 and e to the power 2j theta. Now 1 by 0 is infinity into e to the power of minus 2j theta. Now for C4 contour, it is traveling from minus 90 to plus 90. So this theta is going from minus 90 to plus 90, and this minus 2 theta will go from plus 180 degrees to minus 180 degrees. We multiplied this with minus 2. And when we will draw this C4, the magnitude will be infinity and the phase will go from plus 180 to minus 180. So this is 90 plus 180 plus 270 plus 360. This is minus 270 minus 180 minus 90 and again minus 360. So this is traveling from positive to negative. From positive it will decrease and it will go to 0. Then again from 0 it will go to minus 180. That means it will go from plus 180 degrees. Then it will decrease to plus 90. Then it will decrease to 0. Then it will decrease to minus 90. Then minus 180. So this is the contour of C4, which is in clockwise direction. So in the final Nyquist plot, we will draw every contours in the same graph. So we got C1 as this. It is coming from infinity. And C3 as this. And C2 is this in anti-clockwise direction. And this is C4, which is having magnitude is equals to infinity in clockwise direction. So finally we got every C contours in this. This is C1, this is C3, this is C2, and this with infinity radius is C4. Now if in the question they ask to tell the stability of this system, then we will take a point which is minus 1 plus 0j here, and we will check how many encirclements are there. To check the stability we have this formula, n is equals to p minus z. So here p is the open loop poles which are on the right half side of the imaginary axis, but there is no pole on the right half of the imaginary axis, as you can see in the main question. That is here we have no imaginary axis on the right half of the plane. So we have p equal to 0, and now for n we will check the number of encirclements. So here this is coming from infinity and again going to infinity, and these both will touch each other at infinity. So this is one encirclement which is in clockwise direction. Then this with radius equal to infinity is also encircling this point. This is also in a clockwise direction. So we got two encirclements which are encircling this point, that is minus 1 plus j. This is the standard point. This point doesn't change while checking for the stability of any system. So here n is equals to minus 1 and minus 1, because this is in clockwise direction, so we took minus 1, and again this is also in clockwise direction, so again we took minus 1. So n is equals to minus 2. So if we substitute in this equation, n is equals to p minus z, that is minus 2 is equals to 0, and minus z, minus minus will get cancelled, and we will get z is equals to 2. So this given system is not stable, because this z should be not equal to 0 to be unstable. But when z is equals to 0, it will be stable system. So to get the stable system, z should be equal to 0, and if z is not equal to 0, it is unstable. Hence, this is about the stability of the system. That's it for this video. If you understood each and every part clearly, then don't forget to click that like button and subscribe to my channel for more such videos. Yeah, thanks for watching.